Hi there. In this section, we're going to look at the fundamental theorem of calculus, which is a really theoretical section. So just try to keep up. You guys aren't really required to do a lot of proofs of theorems because you could just look them up, so I'm not going to ask those. But just remember that I can ask you conceptual questions about the meanings of all the stuff that's in this section, even though the actual homework is quite easy. So let's jump right in. Just keep that in mind, that a lot of the concepts you should really try hard to understand. All right, so one thing I want to open with then is that this fundamental theorem of calculus relates derivatives and integrals. And what we do is we have this expression here. And I know this is a weird looking thing. So this is a definite integral if x is a number, right? So we're saying g of x is the area under this function between a and x if x is a number, right? However, we can also treat this number as being a variable. And that's what we're going to see in this section. What happens if we treat x as a variable? What happens to this function? What does it do? What does it look like? Oh, let me move over here. Okay, so what happens if this is a variable? So a couple things. So g depends only on x, right? So even though there's a t over here, t does not appear over on this side. That tells us we can use any letter here. Generally speaking, we don't like to use x over here because we like to reserve x as our independent variable for g. But I've seen lots of different expressions over here. I've seen u and w and y. So just on the homework, whatever letter you see there, it's just, we call it a dummy variable because it ends up going away. It's like a stand-in, like a crash test dummy, right? So the first thing I said was this bullet. If x is a fixed number, so if x doesn't move, then this is an area. But if we let x vary, then what happens is this area varies, but it's a function of just that second number, right? When we did definite integrals from a to b, the idea was that a and b were both numbers. But what if b is allowed to move around? Remember, this variable t, this is just the axis that b is on, okay? And if we call b x, then x is just the numerical value, okay? So we could call this an x if we want, but that's generally not a good thing to do. So let's see how this works. This picture pretty much tells you everything you need to know, and this little box. So if f happens to be a positive function, then g of x can be interpreted as the area under the graph of f from a to x. Well, that's all we want to do, right? And again, go back and look at the formula. That's all we want to do. We just want this to represent the area of that blue region under the graph of f of t between a and x, right, which is this. So here's f of t. We're on the t-axis, and this is the y-axis, but these letters can be anything. And a is a fixed value, so we're saying it starts somewhere. And then where does x go? So what you want to think of is that g is the area up to x, or the area so far from a to x. So it's sort of like a running total. It keeps track of what's happened so far. So we're going to jump right in and do an example. So the example here is this function. And so this is f, and we want g of x to be the area so far. So we want it to be a running tally. As we move x, what happens to the area between the curve and the x-axis? So we're going to estimate a bunch of points along. Then for part B, we have this like weird curve, so we're going to use the midpoint approximation to find that. We're going to talk about the maximum and minimum on this interval, because we're on the interval 0 to 21, right? 0, 21. on our t-axis, and then sketch a rough graph. So this is all stuff that you should be able to do when the exam rolls around. Even though a lot of the homework is multiple choice, please make sure you're practicing this stuff at home. All right, so before I jump into the answer, let's make sure we really understand this. So make sure that you can see that this has the proper form. So the form is this form here. A is allowed to be any number. Okay, so just keep that in mind. It doesn't matter what A is. Just A is not allowed to change. It's not allowed to move, right? So here, A is 0. So that just means that we're finding the area from 0 to whatever that top number is. So when we say g of 0, 0 is x. That means we're finding the area from 0 to 0. Well, we saw in an earlier section that the definite integral from a to a, so from any number to itself, is always 0. So that's just a rule. So you just plug it in, right? I could put the most complicated expression in the universe in here. If it's the integral from 0 to 0, it's automatically 0. If it's the integral from 3 to 3, automatically 3. Automatically 0. So no matter what, as long as we're putting two of the same number in here, it's going to be 0. Now let's look at the next one. So now we're looking at this little green triangle, or sorry, this little blue triangle here. So g of 3, that's the area under the curve from 0 to 3. So we start at 0 and we move over to 3. So what happens here? Well, this is a triangle, right? So it's 1/2 base times height. The base is 3, the height is 3, so you get 4.5. So keep in mind that when we say g of 3, we're saying the area under the curve from 0 to 3 of this function, right? But remember, this function is a function of whatever this top number is. So as we start to move to the right, the area so far as we move to the right is going to change. Let's look at the next one here. So now we're tacking on this new piece, but we're still doing the area so far. So g of 6 is the area from 0 to 6. So what happens is we always just take our previous areas. In other words, we've already computed up to 3. So we're really just looking at from 3 to 6. This is another triangle, but this time, because the function is below the x-axis, we subtract the area, right? We saw that in a previous section. This is very similar. The area itself is still positive. We just subtract the area. So even though this area here is 4.5, we're subtracting it because the function is negative. So you just take your previously computed value, which is 4.5, right? So g of 3 is 4.5, minus 4.5 is 0. So all we're doing is every time we move over, we're going to take whatever we previously computed and just compute a little bit more. So what happens with g of 9? Well, we tack on a little bit more area here, right? We're going from 0 to 9. Well, that's just our previously computed bit, g of 6. And then we're going to tack on this new bit. So up to 6, it was 0. And now we're subtracting another 4.5 because we have another triangle that's the same size. So we're actually, the value for g of 9 is actually negative at this point. So the area up to a certain point is allowed to be negative, right? Because it's a cumulative effect of everything so far. What happens when we go to 12? What's going to happen? Well, we're tacking on another triangle of size 4.5. So the area so far, from 0 to 12, take our old value, add 4.5 because it's positive, and we're back to 0. So just stopping here, you can see that this makes sense. That this is very geometric, that the sizes of these two triangles is the same as the sizes of these two. So the positive and negative areas cancel out when we look at the cumulative effect. What about when we go to 15? What's going to happen? Well, we still, you set it up the same way. It's still the definite integral from 0 to 15. And we take our old value, g of 12, plus that new bit, right? So we're just adding that little bit right there. This is a sideways trapezoid, so I'm just using the trapezoid formula. It's 1/2 big base plus little base, so the big base here is 6, little base is 3, times the height, which again, it's on its side, so it's a width. So you get 13.5. Now we're going to 18. It's another trapezoid. Right, so we're tacking on this little extra trapezoid. So we take our old amount. So we take this part, add that part, type it all into your calculator. You get 36. Nothing fancy happens here. Now, so that's the end of part A. For part B, this is awfully difficult to estimate this quantity. So what I did is use the midpoint rule, and I said to myself, where's the midpoint of this interval? So the midpoint of 18 to 21, again, we're looking at part B. Part B, we have to compute g of 21, but we have to tack on that little extra bit. So what I did is I just said halfway between 18 and 21 is 19.5, and I said, where's the function at 19.5? It looks like it's right about there. Right about there. Right? And then I just tried to estimate the height. And I said to myself, it looks like it's about 1/5 of the total of that little square. It is a square, it's just stretched out, okay? These are 3 by 3 on the side. So I was like, it's 1/5 of the way from 6 to 9. So that's a distance of 3 right here. So 1/5 of 3 is 0.6, so I called it 6.6. So that was how I estimated that value. Well, here we have a rectangle, right? That's a rectangle. So so to find g of 21, I tack on g of 18. So g of 18 is all that stuff so far, summed up. Add a rectangle with height 6.6, base 3, and I got 55.8. So you have a couple of these on the homework. Just keep in mind that on a test, I can ask you stuff that looks super wacky and weird. You got to use some geometry, and you have to know this definition of this g of x function. You got to be able to use it, because we don't use it again after this section, the whole rest of the class. This is the last section we use it. All right, so we did part A and part B. Now let's go ahead and just do part C while we're here, so we don't have to peek ahead at the answers. Where is G? Where does G have a maximum and a minimum? So if you look over here, it makes sense that the maximum would occur when the most positive area was added and like the least amount of negative area. Well, that's G of 21. That's our maximum. Right? Because so if you start like here and just look at the whole thing, you know, here the value of G went up, down, down, up, up, up. But even though the slope of this is negative, we're still adding a positive amount of area. So don't think of derivatives, okay? We're going to connect this stuff to derivatives later. Think about areas. How much area are we adding? Well, if you keep adding positive areas, then the last thing you do is going to be your maximum, and that's true. And where's our minimum? Well, we can see it's G of 9, right? It's negative 4.5. So what was going on back there? Well, just let's do the whole thing again. Up, goes down, goes down. This has to be the minimum because every other thing that we add is adding a positive amount of area. So this is the last negative area we added, so that has to be our minimum. And it's always going to work like that. All right, so went ahead and did that for you. Right, so when x equals 9, we got a minimum. When x was 21, we got a maximum. Now, how do you draw these functions? So the way I want you to do it is plot points and then fill in the details, similar to sketching derivatives. So what I did here, is I just plotted every point from the previous slide, right? I plotted 0, 0, 3, 4.5, 6, 0, 9, negative 4.5. I just plotted all those points. And then I just clicked around until I got a nice function. So I built this in PowerPoint. PowerPoint isn't the best isn't the best program ever, but it will draw curves. And there you go. You have a really nice curve. That's something you could sketch by hand. On the homework, make sure you're doing this. I guarantee you'll have to do this on a test. So make sure you can do this problem. There's one other one on the homework. Again, a lot of multiple choice. Just make sure you can actually do this. Okay, let's keep rolling. Let's do another one right back to back. So here we have f of t equals t. A is 0. And then we're going to find g of x defined by this formula. This is the formula we saw earlier. And interpret the result as an area. So when we have this expression, we can interpret this as the area up to x. Now, for this particular problem, a is 0, right? But it's still the area up to x. Like, a is still a variable. But for this particular problem, we're just saying that this starts at 0. So this area, right, this is just a triangle. And because we're given in the problem that f of t equals t, if we plug in x for t, right, then we get f of x equals x. And if we plug in 0, we just get zeros, right? So it passes through the point 0, 0, and passes through the point x, x. So for any value of x, g of x is the area of the triangle with base x and height x. So we just plug it into the formula of a triangle, and you get the answer. So why did I do such a seemingly easy problem? So one thing you want to notice here, and some of you may have already noticed that, is that if our function is f of x equals x, right, that's the derivative of this, right? So the question is that a coincidence, right? Did I pick this problem just because the area up to x is the same or gives us a function whose derivative is the original function? So does that always happen? So to figure out if it always happens, let's actually go back and look at our previous problem. Let's go back and look at this. So if the derivative of this should be that, does that make sense? Let's find out. So if the other function is the derivative of this, where is the derivative 0? Here at 3 and at 6. 3, 6. Remember, it's the area up to, right? And so you can actually go through and match up all these points. And you'll see that if you take the derivative of this function, you do in fact get this function, which is pretty interesting. All right. So we left off here. So that's something you can actually check. Anytime you had a derivative graph, if you go the other direction, you get an area under the curve graph. And it turns out that this always happens, and it's called the Fundamental Theorem of Calculus, Part 1. So I just call it FTC1. So the idea here is that in the previous example, we had g prime of x equals x. So that was actually our function, right? And so g is defined by this expression, and that expression just happens to be an antiderivative. So let's talk about why this might be true, and then we're going to prove why it's true. So let's look at this picture, right? So this is just a generic picture. And this is the area under the graph of f from a to x, right? This is the picture we saw earlier. So how can we like rename stuff on here so that we can turn this area into derivatives? So that's what we're going to do. So if we have a positive h, so the idea is we pick x, right? So just make sure you see that this is the same picture, right? Here's a. A doesn't even matter where this thing starts. We're just looking at x, right? So here's x. So the idea, if we start at x and move a little bit to the right, we just call that x plus h. So for a positive h, so if we're moving to the right, then g of x plus h minus g of x, so try to stay with this, is we're taking the area from a to x plus h minus the area, because remember g of x is the area from a to x. So we're taking like the area up to this point minus the area up to this point. So what's left over is just the difference. So now we have a little rectangle, right? And this rectangle is approximately equal to the area of the rectangle with height f of x and width h. So because h is very small, obviously we're going to take some sort of limit, right? So h will get smaller. So we have g of x plus h minus g of x is approximately equal to h times f of x. So h is the height, well, the width, because it's like on its side. And then f of x is the height, right? So here's f of x. So here's our rectangle. H times f of x is this area. So this area is this rectangle, and it's also the difference of g of x plus h and g of x, right? So g of x plus h is everything from here to here, and g of x is everything from here to here, right? So this is where we left off on the previous slide. So we can divide both sides by h. Now it looks like a derivative, right? So you guys should be recognizing this as some sort of derivative. So we would expect that if we take the limit as h goes to 0, then that should give us f of x, because this left side is definitely the derivative. But we have to prove that this right side gets closer to f of x. Even though it's believable that that's true, we need to prove it. And it turns out that this is true even when f is not a positive function. So that's really important, because it's going to allow us to define this integral as something other than just subtracting a positive area. We can actually sort of think of it as a negative area. All right, so here's the full proof of the FTC part 1. So it's all the stuff that we just talked about, right? And then we're going to prove it. So f needs to be continuous on a closed interval, and this function needs to be defined on the interval. And if it's defined, then this function is continuous, this function is differentiable, and the derivative of this function is just f of x. So this surprises a lot of people, because you look at this thing and you say, well, this is the area from a to x of f of t, just on the axis. So we're measuring how much area we're adding as we move to the right, and encoded in that is information about the slope of the area function. Like we're actually adding slope of the area function. So we're kind of measuring how fast are we increasing area. That is a slope, right? So if g of x is our area function, the speed that the area changes, or the rate of change of area, is just distance, right? And that should make sense based on what we've done with position and velocity and things like that, right? But we still have to prove it. All right, so we already set all this up. So here we're just defining this very rigorously. So this is the area from a to x plus h of this function minus the area from a to x of the function, right? So we just have two different areas from a some distance to the right. And what we're going to do here is we're going to split this using our definite integral property. We're going to go from a to x and then add from x to x plus h. And what that's going to allow us to do is, because this function's continuous, we have a copy of this, and this is just going to drop out. So we're just defining it this way, right? This part here cancels this part. So this part here is equal to this. Now what we want to do is divide both sides by h. And this shows you why it works, even if the function is negative, and even if h is negative. This shows you why it works. There's no inequalities here, it's just equality. Next step, we have to assume that h is positive to do the next part, okay? So we have just, here's just any old wiggly function. Here's x. Now we're going to define 2 points, u and v. Okay? Notice that just for this particular example, u is just not a special place in the graph at all. But v happens to be the right endpoint. It doesn't matter if one of these is a left or right endpoint or not. It doesn't make any difference. It's just for this particular example that happens. So we know f is continuous. Then we have the extreme value theorem that we saw in section 3.1 that says there are numbers u and v in the closed interval. So we're just closing off the interval x to x plus h. And we're saying that this function attains an absolute minimum and an absolute maximum somewhere in the interval. No big deal, right? But now we can use property 8 of integrals from the previous section. And we can build like this, we can build this construction that uses two rectangles. So here's the big rectangle. So the area has to be smaller than the big rectangle and bigger than the small rectangle, right? So here's capital M times H. Remember, H is that whole width. Oops. And here, the orange one, I guess, is small m times h. Now that we have inequalities, I bet some of you guys can figure out where we're headed with this. But before we do that, I don't like this thing. This is a very clunky thing that's hard to work with. So what we're going to do is we're actually going to replace m and lowercase m and capital M with their function values. We're allowed to leave these as m and as big M and little m, but remember that these are variables based on u and v. And as h gets smaller, because we're going to take a limit, as h gets smaller, u and v are going to change, right? Those are variables, right? The lowest point on that little interval and the highest point in the interval they're gonna move around. Whereas when we write m and m, you usually think of those as numbers that don't change. So it's just a different way of writing. Now we divide through by h. Easy stuff, right? And now here's the critical step. We have an alternative expression for this, right? It's back a couple slides. Let me show you. We can take this whole thing and plug in this. So that's what we're going to do. Right? So we substitute in the expression on the first slide of the proof. So we built this using the fundamental theorem of calculus. Right? Just like defining the area up to this certain part. From here, it's all stuff we've seen before. Now we can tack on limits. right? So now we take the limit as h goes to 0. This limit is the derivative, so we know what's going to happen here. But what's going to happen here? If h is positive and h goes to 0, what happens to u? And what happens to v? So let's go back and look at that picture again. So h is positive, so h is to the right. What happens as h starts to get smaller? Where is u going to go? And then as h gets smaller, where's v going to go? So we're bringing the whole thing together. Well, as h gets smaller, u is getting closer to x, and v is getting closer to x. And this is a continuous function. So what that tells us is that the limit as h goes to 0 of f of u is the same as saying u approaches x. Right? This is just logic. This is not like a big algebra thing, right? If the interval gets smaller, u has nowhere else to go except to get closer to x. And because this is continuous, we can plug this in. So the limit as u gets closer to x is f of x. What about on the other side? So u is just somewhere in the interval and v is somewhere in the interval. Same thing. The limit as h goes to 0, v gets closer to x. So we just plug in x, because this is a continuous function. We plug in x, we get f of x. So that gives us this. This thing in the middle is the derivative of g. And from the squeeze theorem, this is f of x, this is f of x, so this has to be f of x. So the derivative has to be f of x. So it's pretty nice proof. Long proof, sorry about that, but really nice proof. This is what we're going to use to prove the fundamental theorem of calculus part 2 here in about 5 minutes. And the fundamental theorem of calculus part 2 is what we use to do work for the rest of the semester. We don't do this stuff the long way after this. All right, so let's use the fundamental theorem of calculus 1 to find the derivative of the following function. So we're going to use what we just saw directly. All right, so let's just start with part A. So first we need to check that g of x is in the correct form. Sometimes you're given the function and it might have like letters mixed up or numbers in the wrong place. Just make sure it looks like the integral from a to x of f of t dt. Now, the letter names don't matter. This has to be a number. This has to be a variable, any variable name. And these can be any variable name. They have to be the same variable name. And this letter has to match this letter. That's it. That's all we need to check. So we clearly have that, right? So here, a is 1, x is x, and the function f of t is this 4 over t cubed plus 6. That's our function. So the fundamental theorem of calculus says, so part 1, says the derivative of this is just this function, well here it is, f of t, with every t replaced with an x. Done. That's all you gotta do. And again, if you're wondering why it works, we just proved why it works. So if you're not understanding this, just go back and try that proof again until you can get the hang of it. It's not an advanced proof. There's no advanced algebra. I mean, I only proved it if h is positive, but because these limits exist, then if it's negative, the limits have to be the same on both sides. So I kind of skipped over that just because I'm trying to keep this video under 45 minutes. So there you go. So that's the way you do a problem like this. Now, some of you might go, so I'm looking at the original problem here and go, oh, that's easy. I just take the top thing and plug it in here and I'm done. That is not correct, as we're going to see in the next problem. So for this problem, that's how it works. But I want you to break it all the way down. Because for this one, for the second one, it gets more complicated. Actually, let me go back and look at the... Here, let's look at part B. Let's make sure we understand what this is saying. So here we have y equals the integral from 2 minus 3x to 3 of t cubed over 1 minus t squared dt. Keep in mind, these don't have to be t's, these can be any letter. So the first thing you want to notice is that we don't have an x here. You need to get a single variable in the top somehow. Okay, so that's the first thing we're going to do. We need to replace this expression with a different expression so that I can get a variable here. It doesn't have to be x, it just has to be a variable. All right, so let's see how to do that. So here's part B. So what I'm going to do is the variable I want to put up there, I'm going to call u. Okay? And I'm just going to say u is 2 minus 3x. So that big expression that has a variable in it will now reduce to a simpler expression. Now, du dx, the derivative of this with respect to x is negative 3, right? Right, you can just take the derivative of both sides with respect to x. Then there's one other thing I have to do. We're trying to find the derivative of y with respect to x. But I need to use this du dx. So the way this works is we're going to make y into a function of u. Then we're going to take dy du. And then the chain rule is going to give us a du dx, which is this part, which is what we want. So we're building this thing so that the chain rule can give us the answer. There's no other way to do this problem. All right, so here we go. So we take the derivative of the original function here. So it's dy dx. Remember, this whole thing was called y. So dy dx is just d dx of this whole thing. Now, what I'm going to do is I'm going to use this substitution. I got to get rid of this 2 minus 3x. It's just causing trouble. So I'm going to replace the 2 minus 3x with a u. Nothing else changes for the first step, right? So now it's d dx of this expression. But now we have an x and a u and a t. Don't worry about it. We're going to fix that. Next thing we do, I reverse the limits of integration. Here it went from u to 3. Here I switched it to go from 3 to u. And I put a negative out front using the property from section 4.2. There's a property that lets us do that. Notice that nothing else is different here. Now I'm going to try to use this chain rule. So instead of d dx of this, I'm going to take the derivative with respect to u here. So now we have dy, this is y, du. But I have to multiply by du dx because of that chain rule. So when I replace dy dx, this is dy dx, with dy du, I need to tack on the du dx from the chain rule. That negative stays out front. Next, I use the fundamental theorem of calculus part 1, and I replace du dx with its numeric value, negative 3 here. So now that I have so the derivative of this expression, notice this variable matches this variable. That has to happen. As soon as this matches that, I can use the fundamental theorem of calculus. This has to be a number. This has to be a variable. When that happens, you just replace this entire expression. Again, it's negative. Just leave the negative out front. I replace this entire expression with this thing with u's instead of t's. And then this becomes this. And now we're almost done. Now we just translate everything back to x. So wherever you see u's, put in the original expressions, and we're done. Don't simplify this. Just leave it. Because this simplifies horribly. And the only reason you really want to simplify is for stuff to cancel. Nothing can cancel here because of this 1 minus. So don't even mess with it. So, not an easy problem by any stretch. But between this one and the previous one, this is a direct application of the fundamental theorem of calculus part 1. This is a little more indirect, and you have to do some manipulations to get it to look right. All right, let's keep moving. Got one more example, but we do have another proof coming up. Now we're going to prove the fundamental theorem of calculus part 2. So if f is continuous, then the function so the definite integral of f of x dx is f of b minus f of a. So capital F of b minus capital F of a, where f is any antiderivative of lowercase f. This any is part of the proof. You'll see why it is. Don't get too wrapped up with this stuff. Just pick a number and go with it. You'll be fine. You'll be absolutely fine. So let's make sure we understand what this is saying. That a definite integral not only is an area under a curve between a and b, but it's the antiderivative, right, of that capital F function evaluated at b and the capital F function evaluated at a. And you can, again, once we do the proof, you'll see why this is true. Because this might be surprising, that all you have to do is do an antiderivative and plug in two numbers. It makes everything so much easier. Not easy, just easier than what we just got done doing for the whole day. All right, so let's prove this guy. So we're going to start with g of x is the integral from a to x f of t dt. So that's kind of what we're basing everything on in this section. So the fundamental theorem of calculus part 1 told us that g prime of x is just f of x, if we can get it in this form, right? Any other antiderivative, capital F of x, differs only by a constant on the interval. Okay? So let's think about what this is saying, right? So the antiderivative back here, right, is just the antiderivative of lowercase f. So when we say any other antiderivative of f, we're talking about just whatever this function is. So that tells us that g, without the prime, just g, is indeed an antiderivative. And what we do is we just write it like this. F of x is just g of x plus some constant. So what we can do is we can put x equals a into the formula. So whatever this lower bound is, we can just call that the left endpoint of this area up to x function. So when we plug a in here, we just get the area from a to a. We know that's 0. But when we plug in b into the formula, watch what we get. Okay? So we have f of x is g of x plus c. So I'm just replacing f of b with g of b plus c. I'm replacing f of a with g of a plus c. So we're just kind of like building this construction and saying, if we have an a and a b and plug them both in, what do we get back? Well, this is the area up to b. Remember, g is our area up to b function, plus some constant, minus the area up to a, plus the same constant. And we can see what's going to happen. These c's cancel, because they're the same constant. And that leaves us with g of b minus g of a. But g of a we just proved is 0. So we just get g of b. And g of b, by the definition that we set out to set up, was exactly this thing here. So what we've done is we've taken this g of b is the area from a to b f of t dt, and we've taken the x out of it, right? What we can do now, because this is a definite integral, what we saw in a previous section is that definite integrals don't care what the variable is here. We can go back and put x in there. So it just, from this point forward, if we have a definite integral, it doesn't matter what the variable is. So here's an x, here's a theta. Doesn't matter. It only has to be t when we're doing those proofs. Or when you're doing like the first part of the homework from this section, there'll be some t's. But it could be any variable. Could be a u, could be a w. It's just usually not an x. All right, let's do these. So let's use the FTC2 and see how this works. So the first thing you want to do is find any antiderivative of f of x. Right? So for this one, f of x is just this, right? Radical x. So radical x is just x to the 1/2. What's the antiderivative? Well, we did that in section 3.9. You just increase the power by 1, divide by the new power, and simplify. So this is our capital F of x. Notice we don't need to do a plus c. I know you guys were thinking in section 3.9 that you need to see a plus c everywhere. But let's go back and look at the proof one more time. Any c, so this capital F is just something plus c. Any c that I add here, no matter what the number is, it's going to get subtracted. So if I choose to make it plus c minus c, no matter what happens, it gets subtracted. Okay? That's why when we're doing this, don't worry about the plus c. Okay? If you're instructed to find any antiderivative, not a specific one, don't worry about the plus c. If you're told to find the most general antiderivative, you need the plus c. Now we just plug everything into the formula, right? So the integral from 1 to 4 of x to the 1/2 is 2/3. So what we do is you take the upper limit, put it in here, take the lower limit, put it here. So that's just 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2. I factored out the 2/3. 4 to the 3/2 is 8. 1 to the 3/2 is 1. You get 14/3. You're done. So this is a much easier way of doing areas compared to a lot of the stuff we've been doing in section 4.1, 4.2, and even the beginning of section 4.3, right? Finding areas is a hard problem. In fact, we didn't even have a method for finding an area of like x to the 1/2 because we don't know how to do any sort of substitutions with i's and n's. So we have this rule now that makes finding areas much easier. Not easy, but easier. Let's do part B. So here we have our function is secant theta tangent theta. So the antiderivative is just secant theta. Make sure you note that you don't need the plus c. You're allowed to put it there if you want. I'm just telling you you don't need it. So now we use the formula. So the integral, the definite integral from a to b f of x dx. Well, here these are thetas. Again, the variable doesn't matter. So we just plug in thetas. Because remember, on a definite integral, this is just a number. So the variable completely disappears. So here we just have secant theta tangent theta. So when you do the integral, it's just secant theta with b plugged in minus secant theta with 0 plugged in. That's just radical 2 minus 1. You're done. Much easier. So just a couple things I want to point out for problems like this, you need to show exact values. Decimals are not appropriate here on the homework, and on tests they're not going to be allowed either. So just make sure that you know your unit circle because a lot of trig does pop up in this section. So just watch for that. And you have to show a little bit of work. You don't have to show a ton of work. Like, you don't have to show work for the antiderivative. You should just know what they are. From section 3.9, we did a lot of antiderivatives. And just show that you're using the formula. I have to be able to follow something so that I know you're not just looking up the answer. Because these things, in general, are easy to compute. So on a test, make sure you're following the correct steps. That's it. So if you guys need extra help, there's some nice resources here. These animations are pretty interesting. At the very end of this video, I'm going to show you one of these. The Explore It. I'm going to show you the Explore It. The animation's still cool, but I'm going to show you the Explore It. And there's some extra problems here. So let me go ahead and let's look at... so here is... the Explore It for what we've just been talking about. Oop, that's too big. All right, so here we go. So here's how this works. Here is just a just some goofy function, okay? And what I'm going to do is I'm going to slide across, okay? I'm just going to move to the right. And what this thing here is going to do is this is going to keep track of the area. So look here, capital F of x is the area from -2 to x of f of t dt. So this is the, it says x, but it's the t-axis. So look, I'm coming across. So look at what's happening here. When we start, the area is 0. Remember that you always start with the area 0. So let's go to like -1, right? So how much area have we added so far? Well, you can see that there's a little square up here that has size 1. So this is about 1/4 of that area. So that means we've added about 1/4. So the y-coordinate of the of this area so far function goes to there. All right. So now let's go to, let's say right here. So look here. We're adding area as fast as we possibly can. So that means the slope of this should be at its steepest point. Because remember, this is the derivative of this is keeping track of the rate of change that we add area. So now as if I keep going, we're starting to add area more slowly. So this thing should slow down but still be positive. So look, the slope of this line is slowing down, or this function. Slowing down, slowing down, slowing down, slowing down, right? So now we've added a bunch of area. We started adding area more slowly, so the slope starts to even out. What's going to happen to this slope here? Well, I'm going to start to add negative area. And the area so far function is going to start dropping. Right? And so here we're adding negative area at a very fast rate. So this slope should be negative. So we're still adding negative area, so it keeps dropping, keeps dropping, keeps dropping back to 0. Now what else you can do here, so there's all kinds of stuff you can click on here. I just want to show you another thing though. Is down here a little bit farther at the bottom. Where'd it go? Oh, here it is. You can click on this right here, and it'll show you the slope of this area function, this area so far function, and it's going to redraw this because you can see the like tangent slope. See how there's like a little triangle, and then like the tangent is the slope, and all it does is just redraw the original function. So it's pretty cool. So you can go through and just click on different functions and see if you can guess what's going to happen. Like you can turn this off. And you can say, look, we're adding a negative area, so this thing's going to drop. Right? As soon as we start adding positive area, this thing's going to be positive again. All right, what's special about this point here? Well, this is the point where the area so far is 0. That means this and this are the same size. Right? And you just keep going. You can go all the way across. So here, we added a bunch of positive areas, so that's going to be our maximum. Now we're adding some negative area. So we're still adding negative area. So that's going to be either our minimum or part of a minimum, and then back up. And you can check. Where are the critical points of this? Here's a horizontal tangent, crosses the x-axis. Here's a horizontal tangent, crosses the x-axis. Horizontal tangent, crosses the x-axis. And that's how you do it. So you guys can mess around with this. So that's it for this video today. If you guys have questions, you can post stuff on the discussion forum or email me. And I will see you guys next video. Bye-bye now.